Assalamualaikum. We are dentistry students from section 808 under Sir Wan Shahrum bin Wan Saleh.
And the topic for our physics project is the invisible push, Newton's rules of the universe.
In our presentation, we will provide a fine and educational explanation on the 3 Newton's rules with examples and also focus on the static versus kinetic friction force. Let's go!
This is Amni. She is a flight attendant. Looks like she's late for her flight. Amni always carries her luggage everywhere she goes. Literally everywhere. On rocky roads, on pavements, and even on grass. Look at that. She's pulling her luggage with all her strength. That is force in action. But what exactly is force?
Great question. Force is a push or pull of an object that results from the object's interaction with another object. Do you know him? He is Isaac Newton. He is famous as he proposed the 3 laws of motion. The first law states that the natural tendency of objects in motion is to stay in motion, and for objects at rest is to stay at rest, unless it is acted upon an external force that causes the velocity to change. Look at the magic trick. The bottle remains at its place. This indicates that the Newton's first law of motion is applied, and this is what we call as inertia. Inertia is associated with mass. The higher the mass, the higher the inertia, which means the higher its tendency to stay in motion or to remain at rest. Let's see what happens if each bottle has different mass. As you can see, the heavier the bottle, the more it wants to stay still. This is because it has higher inertia due to its higher mass. While the lighter bottle, it moves more easily when the cloth is pulled. This is because it has less inertia.
Hey look, there's Amni.
Beratnya beg ni.
Amni, why'd you take all of those out?
Sebab nak bagi ringan lah dia.
Let me explain to you. As she pulled the handle of the luggage, she deliberately applied the force which abided by Newton's second law. This law stated that force is directly proportional to mass and acceleration. Based on the previous situation, as we decrease the mass, the force applied also decrease. So, it will be easier for us to pull the handle of the luggage with less force and higher acceleration. Let's observe this figure. Force is a vector quantity that has x and y component. The resulting force is in upward and downward direction. Fx and Fy follows this formula. Fx equal to F cos theta and Fy equal to F sin theta.
This is Hannah. She loves playing netball during her free time. Some call her the trick shot queen. Whoa, that's Newton's third law. Let's see what Amni has to say about this.
Newton says, forces in nature always exist in equal path, which means for every action, there is an equal and opposite reaction. As the ball hit the ground, it applies force onto the ground. This is the action. The ground pushes back the ball with the same amount of force, and that's why the ball bounces back. This is called the reaction. From this formula, it is shown that both forces have the same magnitude, but in different direction, which indicated by the negative sign.
Next, have you ever wondered which situation in daily life applies all 3 of the Newton's law of motion? Lift! Correct! The lift applies all 3 of the Newton's law of motion. Let's watch this.
Hasya and Hannah are on their way to the physics lab. Looks like they're using the lift.
As the student enter the lift and the lift is not moving, there are 2 invisible pushes happening here. The students aren't just standing. They are actually exerting a downward action force toward the floor of the lift, known as weight. Weight is represented by the formula weight equals to mass times gravitational acceleration. However, that's not the only force exerted. According to Newton's third law of motion, for every action, there is an equal and opposite reaction, so the floor pushes you right back. That's why they don't collapse into the floor. It's because the reaction force from the floor is what keeps you standing. It's called the normal force. It's always there, quietly holding you up.
Now they're going up to the physics lab. I wonder what happens to their weight.
That's easy. When a lift accelerates, the Newton's second law of motion is applied, which states that force is directly proportional to mass and acceleration. This is demonstrated by the formula F equals to ma. When the lift accelerates upwards, the floor of the lift needs to push harder in order to lift the students up to the second level of the lab building. This means a greater reaction force is applied by the floor of the lift. Hence, the scale shows a heavier reading. This scale reading is known as apparent weight, or W. W is equals to mg, which is your real weight, plus ma, which is the applied reaction force. Look at this. As the lift accelerates upwards, the weight reading on the scale increases.
Oh, the girls are hungry now. They're going down to the cafe. What happens to weight as it goes down?
When the lift accelerates downwards, the floor of the lift doesn't need to push up as much to support you. This means the reaction force from the floor of the lift decreases. Hence, W is demonstrated by the formula W equals to mg minus ma. Hence, the scale shows a lower reading.
Imagine someone cuts the cable. Suddenly, no more upward force from the floor. The lights are blinking. What'll happen to the person in the lift? Oh, it looks like he's floating.
Yes, indeed, he is floating. Now, Newton's first law takes over. This law says that object at rest stay at rest, and object in motion stay in motion, unless acted on by an external force. In this case, the snapping of the cable is the external force. It changes the situation by removing the upward support from the floor. As a result, the students and the lift falling together at the same speed. Their bodies want to stay at rest, but gravity pulls them downward together. As the floor is no longer pushing up on them, it feels like they are floating, but actually they are falling.
Hannah, I'm so hungry. Me too. Let's take the shortcut through the grass to go to the cafe faster. Let's go.
As they were on their way, they spotted someone familiar.
Isn't that Amni, the stewardess? She's struggling with her luggage again.
One, two, but move.
Right now, she's up against static friction force, the force that resists the motion between two surfaces. It depends on two things, which is the normal force and also the type of surface. The static friction force follows this formula, Fs equal to mu s times n, where Fs is the static friction force, mu s is the coefficient of the static friction, and n is the normal force.
Now Amni tries to give one big tug.
Yes, let's go.
And it looks like it worked. Her bag is rolling.
Now that the luggage is finally moving, this means that Amni's applied force is finally greater than the static friction force, which is what is holding the luggage from moving. Amni's big tug has provided a force that was strong enough to overcome the resistance from the grass. Hence, this is what makes her luggage move across the grass field. When the bag is moving, this means that the static friction force is gone, and now it is replaced with kinetic friction force, which is represented by the formula Fk equals to mu k times n.
Now, let's compare bringing the luggage on the grass versus on tiles. The grass is soft, uneven, and bumpy. The wheel sinks slightly into it, which increases the contact and the grip. On the other hand, the tiles are hard and smooth. There is less grip, less resistance, and the luggage glides with less effort. So, it is easier for a person to bring luggage on tiles compared to on grass, as the static friction on tiles is lower than on grass.
So remember, whether it is rough grass or smooth tiles, friction is always there, adjusting to the world beneath our feet, quietly resisting to every move.
In conclusion, physics isn't just something we learn in class. It's happening all around us all the time. Through Newton's laws, we begin to see the forces that quietly shape our daily life.
We don't usually feel it, but every time we are being pushed, pulled, and balanced by the invisible forces. From the floor beneath our feet and the lift that carries us, Newton's laws are always at work.
And that's the beauty of physics. It doesn't shout, it pushes invisibly.